So yes, today we're starting with chapter 4 in the book, chapter 5 in the notes, since we're doing it in a slightly different order. So today we're starting with representations. So let V be K vector space where K is R or C. So we're considering either real or complex vector space, and then the following group. Which we write as GLV, and it's all maps from V to V, such that L is K-linear and invertible. So this is not a matrix Lie group. Before we choose a basis. So after we've chosen a basis, then this is a GLNK where n is the dimension of B. So this goes a bit outside of our definition, but not quite so far. And we were going to treat this GLV basically as a matrix Lie group, but we're going to try to not pick a basis as much as possible. We also have Lie algebra, small GL V, which are then maps from V to V, where X is again K-linear. And this is a Lie algebra with XY bracket being XY minus YX. So works just as with what we've seen so far. The only difference is, again, we haven't picked any sort of basis. Then a representation. So if representation V large pi of matrix Lie group G is the group homomorphism okay, or let me say it exactly right. So a representation is a K vector space V and Lie group homomorphism pi going from G into GLV. So why is it called a representation? Because it means that you can take your group and then represent it as acting on a certain vector space in a certain way. So in this group, we're only working with matrix group, and then this sort of loses some of its effect because it's already kind of represented as acting on a vector space because it's already in the matrix form. And this has more of effect when you think of like just an abstract group. Like if you think of set mod set 4 for set mod 4 set, for example, you can think of them as the rotations of a space. That's a way to represent them, is by 90 degrees rotation. And so this is more in line with this idea of what the representation should be, whereas here you already have them on the matrix form, so it's kind of less impactful. But it's still very important for understanding these types of groups is actually understanding their representation. And this is called real slash complex, depending on whether V is real or complex. So it's important to note that implicitly here we have some sort of structure on V. So of course, obviously, if I have a complex vector space, I can consider it as a real vector space with double dimension, but my GLV is not the same if I consider it as a real vector space compared to a complex vector space. That's very important. So that's the first definition. Now the second definition is if I have G.
Just a question, Alan.
Yeah.
So what you meant by that is that if you have a complex vector space, you require the linear transformation to be C-linear.
Yes.
That is the important thing, right?
Yeah, and so if I look at the complex numbers, for example, as R2, then I have much more linear transformation from R2 to itself than I do have complex linear transformation from C to C, right? So what the GLV means depends a lot if you consider V as a complex vector space or a real vector space. That was what I was saying. Okay, next, if G is a G can be a real or complex, the algebra. Then a complex representation of G is a complex vector space V with Lie algebra homomorphism small pi going from G to GLN, GLV. So again, you're representing it as acting on a certain vector space. And then, but again, here G can be either real or complex, but it's important that for a complex, if you have a complex representation, you need a complex vector space. Whereas for a real representation, you need that both G and C, no, sorry, and V are real. And one final definition, representations V pi and V small pi are called faithful if pi or small pi are injective. So that's when you really get to express the full group or Lie algebra in your larger space is when you have something that's faithful. And they have trivial. So when these maps have trivial kernels. And note that in this course, we'll only do finite dimensional representations. So there are some very interesting infinite dimensional representation, especially one of these matrix Lie groups. So much more. If we did a representation theory on finite groups, then basically we would only worry about finite dimensional representations. It's not really the case for Lie groups, but for now we restrict ourselves to finite dimensional representations. So let's look at some examples. So the easiest one is the trivial representation. And that one was it's just you take any vector space V pi where pi of A is just the identity for all A in G. So that will be a representation. It's the most boring one, but it's still a possible representation. So this will not be faithful at all. For the algebras, the trivial representation is the one that sends all elements to the zero map. So it's not the zero, but of the vector space, but the zero map. So the linear map then maps everything to zero. Then we have the standard representation. Where G is some subgroup of GLN and K. V is then K to the power N, and pi from GL from G to GLV, which is now just GL and K. That's just the identity. So if we have a matrix Lie group, then we have an associated standard representation just given by considering the matrix that's acting on its own vector space. And we can have, similarly, if you have your matrix, the algebra, inside of some GL space of matrices, then you use V equal to Kn and pi from G into GL and K will just be the identity. So that's the two boring first representations we first encounter. Then we see in another representation called the adjoint representation. And the adjoint representation you've seen as follows. Let G be a matrix Lie group with Lie algebra G. Then we have the adjoint map from G to GL, large GLG, defined as add A going to add A. So then the adjoint representation is G add. And how did this add work? Well, if you had add A and then X, it was the map that mapped multiply with X and then A inverse. And this was also inside by the properties of the exponential map. This was also inside of the algebra. And here, in the previous versions and in the definition, we've mostly seen look at representations in like this way here, right? Maps from G into the space. But usually when you describe a representation, it's how does it act on the actual elements inside the space, right? So how What is the thing that an element A does to an element inside of the vector space? So that's why we denote it by the vector space instead of like the GL of the vector space itself. So this is an example of a representation, and the adjoint represent and the corresponding for Lie algebras. We have the small corresponding add from G to GLG. So then 3 frac letters at once. And this is given by add X, Y. Okay, so it's, yeah. It's Y. This was the bracket of add X, Y. And you can see here that I've in all of these I've given sort of a pattern. First, I'm showing what it is for the Lie group, and so I'm showing it for the Lie algebras, and I'm doing this for all of these 3. And that is because, well, we've seen in this previous weeks, we've talked about the relationship between Lie group homomorphisms and Lie algebra homomorphisms, right? And since G is and since GL of a vector space is and small gl of a vector space, these are matrix Lie groups and matrix Lie algebras. Once we've chosen a basis, then we can use our previous results that we obtain to get the following relations. So theorem. If the pi is a representation of G, and its Lie algebra is math frac G, then we have representation V small pi of small g by small pi of x acting on an element V. So V is here in the vector space, and that's given by d dt. And then the large pi of e t x t equal to 0 applied to V. So just as so we've seen that we can do this with Lie group homomorphism to get a Lie algebra homomorphism. Just take the differential at the identity, and the same holds for representations. So this satisfies pi of e to the power x is small e of small pi to the power of x, and if I take add of a, that's right, first a small pi of A x, then this is equal to add of large pi of A of applied to pi of x. So here x is in the Lie algebra and A is in the group. So this is all results we've seen so far, just apply to representations. Let's call this one A, and then the converse is that if V pi is a representation of G and our group is simply connected, then there exists a representation V pi of G such that pi of E of x is E pi x. And this is sort of a bonus result. This is not in the book because this result is in chapter 5 in the book, and the algebras are in, and the representations are in 4. But you can get this from using our results of chapter 5, that we can always integrate the algebra homomorphisms on a to a simply connected Lie group. In both cases, pi, V pi and V small pi are called associated. So we have this relationship between, let's see, let me put a curl on top of that, between these representations of group and representations of the algebras. And as I mentioned before, usually it's then easiest to work with the Lie algebra because that involves just working with linear maps. And then you can check that all of these representations here in my list are associated. Let's see. Okay, so the next part is to talk about the concept of irreducibility. Irreducibility. So the general idea is, if we want to study representations, is that we need to like split them into smaller parts that are convenient for us to work with. Or the idea is that if we want to study all representations, we can always make new representations by adding a lot of them together. So we want to have an idea what are the smallest parts that we can use. So so first we need to look at then the concept of being invariant. So we say that if we have a representation um, then W is an invariant subspace if uh, it is a subspace and pi of a W is inside of W for any A in um, for any A in G. So we call then V and W and then pi restricted to W subrepresentation. And we say and we say that an invariant W is non-trivial if W is not 0. So 0 is always a subrepresentation. It's always invariant if you multiply 0 with something linear. Then you always get 0, or W equal to V. So the whole space is, of course, also invariant. So these are for every vector space. These are invariant subspaces. So we need to disregard those, and then we say that V pi is an irreducible representation of G if V has no non-trivial invariant spaces. So if we have no smaller part that can be made into a subrepresentation, then the group is, then we say that the representation is irreducible. And the search for like irreducible representations is going to be most of what's going on it's most of what's going to happen with the rest of the course. is to search for these representations, find them, yeah, and understand them. So remark, the same definitions holds for representations of the algebras. So we have the same definition of being invariant, same definition of irreducible, and so forth. And the important results related to this is as follows. Theorem. So let's assume that G is a matrix Lie group. And then math frac G is the Lie algebra. And we say that, and we have a representation V large pi associated with V small pi, then V and pi, large pi, is irreducible if and only if V and small pi is irreducible. So if we want to check if something is irreducible, then it's the same as if we check the representation of the group, or if we check the representation of the algebra.
I have a quick question, Alan.
Yeah.
So we had an existence theorem for an associated representation.
Yeah.
So is it always unique?
Yes. So it's yes, it's always unique. It's unique by this formula. I can put let's see. I can put unique. Yeah. So here, I mean, so here it's explicitly given, right?
Okay.
And this is the formula you compute it with. So, but yes, it's yes, it's always unique. So I think we saw that in the other course, that if we had if you had a Lie group homomorphism, then it was associated with one unique Lie algebra homomorphism. And then conversely, if you are connected, then you have uniqueness the other way around. You can, of course, do shenanigans with non-connected stuff, but for connected, there's every you can only have one Lie group homomorphism corresponding to a Lie algebra homomorphism. We can do the proof of this, because then perhaps that will answer the question. So the proof that if one is irreducible, then the other is irreducible, right? It's basically, oh, sorry. Thank you, Anna, for this question, because that made me realize that I forgot connected here. Because that's very important. Because otherwise it is not true. So otherwise you can have things that are irreducible. So you would have just this way if G was not connected. No, the other way around, sorry. So it's easier to be, so invariant here means invariant here. So yeah. Yes. But okay, they are equivalent when G is connected, and why is this the case? Since A in G can be written. So what we talked about last time, or at the gathering, if you have a connected Lie group, then all of your elements are product of exponentials. So large pi of e to x1, e to xm, e to pi 1, x1, e, not pi 1, but just pi, small pi, x1, small pi, x m. And so here is then the answer to the one-to-one correspondence, as we saw earlier, because once I know the small pi, that determines what the large pi does in all of the elements. And that means that since like e to pi 1x, what is that? That's the sum, j equals 0 to infinity, pi x to the power j over j factorial. So if j of x sends w into w, then e pi of x sends w also into w. And then conversely, if large pi sends a of tx from w into w, then d dt pi e of t x at t equal to 0 applied to w will also be inside w. So again, it's sort of the same results here, so that if we have a connected Lie group, then all elements are products of exponentials, and you can just check what exponentials does, and then you see that you have the same invariant subspaces, and hence the same definitions of what it means to be irreducible. We continue in the second part with isomorphism of representations. So definition, let v pi and vw sigma be two representations of G then L from V to W is called an intertwining map if pi of A of LV, no, sorry, and the L needs to go here, LV is equal to sigma A of LV for any V in V, A in G. So in other words, it's intertwining if you can take if you sort of think of this as like acting on this vector v, it's trying to change this vector v in some way. If it's the same, if you move it to the other vector space and then act on this thing here, then it's called an intertwining map. Other names, morphism of representation, or an equivariant map. So these are all used. I don't know if so personally, I don't think intertwining is the most popular. So these two particular equivariant map is the most used in literature, I would say.
Alan, we require L to be linear as well, right?
Yeah. Yes. So yes, so L is then a linear map, and it's called an isomorphism of representations if L is invertible. So this is how we consider two representations to be the same, is that we have this intertwining map and we can invert it. to get a new intertwining map, then we say that two representations are the same, so they are isomorphic. And the same definitions hold for representations of Lie algebras. So let's see if we have time to do an example. So we can consider G as SO3. This has a basis that looks like, let's do 1/2, 1 minus 1, 0, 0, 0, 0, 0, y minus half, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, and set equal to 0, 0, 0, 1, 0, 0, minus 1, 0. See, did I do I want to keep these names or switch y and z? So if I take x with y, then I get minus 1 there. And if I take y with z, then I get 0. I also get minus y. Let's see. Okay, this is fine. So I'll just keep these names. So then x, if we took the leave and put 1/2 here. So if we now take the Lie bracket of x with z, we have zeros here on the first row, and let's see, I should perhaps remove these 1/2s. Yeah. Sorry about this. So if I now have x with, yeah, I should definitely switch x and y. Sorry, set y. So now x with y is equal to set. Y with set in the spaces. Is that minus x? Yeah. Let's see, x with y set, y with set is x. Yeah, y with set is x, and set with x is y, like this. And now if we look at consider the adjoint representation. If I look at add x in the basis x, y set, so I'm going to write it like this. So here's the output x, y set. Here's the input x, y set. So for x, I'm getting nothing. And then if I insert y, then add x, y will give me set. So that's 0, 0, 0, 1. And then if I'm x with set with y is y, so then I get, if I change the order, I get a 1, minus 1, 0. So that will be my add x represented here on as acting on the Lie algebra. That's the matrix form. And similarly, if I look at the matrix here of add y, x, y set, x, y set, then, okay, obviously it does nothing to y. Then together with x, it gave us minus set, so it's 0, 0, 0. And then to get x, y, and set give us x, so that's 1. Here we have 0, 0, 0. And now finally, with x, y set and x, y set here, obviously I get nothing if I use the add map on x. On set, sorry, then on x I get y, 0, 0, and then minus 1, 0, 0 here. So we see here that if we started off with the Lie algebra of matrices, and then we did its add representation, and then we looked at how they look in the bases, they basically look like the same matrices all over again. Hence, if R3 pi is small pi, sorry, is the standard representation and SO3 add is the adjoint representation. These are isomorphic. So more specifically, if I look at this L map, this L has to send A1, A2, A3 into, okay, and then I want X to do the same. So X sends Y to yeah, so this is what add X does to Y. So to a1y plus a2 set a3x. So this is how you can construct an isomorphism of the algebras between these two representations. Okay, and then we quickly have a theorem with the same proof as earlier. So that if v pi large pi and w sigma are associated with v small pi and v small sigma, then v and large pi, then the group representations are isomorphic if and only if the Lie algebra representations are isomorphic. So if we want to check if they are, and again, I assume I need G connected. For this. So as long as we're studying connected Lie groups, then studying if two representations are the same is the same as checking if it's the same thing to check it on the group level as it is to check it on the Lie algebra level. And then again, the reason the proof is the same is just as before. If we have a connected Lie group, then it's a product of exponentials. Then there are a couple of topics that I don't have time for today. So read for yourself. If the pi is a complex representation of a Lie algebra, of a real Lie algebra, it can be extended to its complexification. It's fairly straightforward. And then definition of unitary representations. Because these are also quite important going forward, but they are straightforward definitions of what it means to be unitary in the setting. Now let's talk a bit about operations on representations. So in what follows, we will define Lie group version and the algebra version. This will always be associated. So meaning that if I start off with associated representations, the new representations that we'll make using the direct sum, the tensor product, and the duals will also be associated. And it will be your job in the exercises to show this. So let us start with the simplest operation. It's the direct sum. So on vector spaces, what is this? So on vector spaces, if we have V1, V2, Vm vector spaces, then the direct sum written as this with this plus here is the collection of m vectors where vector j is in vector space Vj, and then scalar multiplication here is just defined by scalar multiplying each of the elements. And if you have two vectors, then you define their sum as just the sum in each element. And the dimension of the space will then just be the sum of the dimensions of the individual space. So if you think of the way you would make Rn from just R by putting different real coordinates together, this is the same, but for general vector spaces. And then for representations of groups. So if we have V1 pi 1 to V m pi n m, then we define a representation on V1 direct sum Vm by, if we have pi direct sum going all the way to pi m of an element A, applied to the m tuple V1 to Vm, then this is just applying each representation to each element in the M tuple. Vj is in Vj and A is in the group. So if we have a direct sum, then that's just using each representation on each of the elements. So this is the easiest one. Continue. So let's a group. Let's say for representation of the algebra, it's more or less the same. We have pi 1. Well, it is exactly the same to x v1 vm, and that's equal to pi 1 of x v1 small pi of vm x vm. So this one is exactly the same for the same way of generalizing it as for the Lie group and the Lie algebra, and then it will be your exercise to show that, okay, if you start off with all of these associated, then in the end you get something associated when you take the direct sum. So next thing we have tensor products. So what are tensor products on vector spaces? So the easiest way to define them is as follows. Assume that V and W are vector spaces over either the real or the complex numbers. Choose a basis E1 to En of V and F1 to Fm of W, and define V tensor W as the span over K of all of these elements E, I, and then we use this tensor symbol, EFJ, such that I goes from 1 to n, and j goes from 1 to m. Okay, I probably shouldn't use I here since, so EK, since I can be the imaginary unit, so EK to ENFJ. So we just make these elements symbolically, and then we define a vector space that is the linear span of these elements. And that means that by definition, the dimension of the tensor W is n times n over here, because that's the number of basis elements. So in other words, that's the dimension of V times the dimension of W. So if V is an element in W and small w is an element in large W, we write V as a sum j over j from 1 to n, Vj, Ej, W, sum k 1 to m, wk, fk, then V tensor W is the sum j equal 1 to n, k equal 1 to m, Vj, Wk, Ej tensor Fk. So if I have an arbitrary element, I can define their tensor product as just being their expression in the spaces used written, and then each of the coefficients in pairs becomes sort of the elements here. So note that with this notation, if I have, if I have W tensored with V tensored with CW, that's the same as having CV tensor with W, or C times the tensor product on V and W. So the tensor product is then linear in all of the coordinates with this definition. And why do we like tensor products? Well, tensor products are very, very nice because they allow us to look at multilinear maps and linear maps between vector spaces, all as elements in kind of the same vector space. So, or as either belonging to a vector space or dual of some given vector space. If B going from V to R is a bilinear map, then we can consider it a linear map from BV to R. So now it's just a one linear map from a vector space by B hat B tensor W equal to B V W. So it allows us to consider multilinear maps in the same framework as linear maps. Um, so if you've seen the tensor product before, it usually so at least when we teach them Bergen, we don't have a linear algebra 2, so we don't have like really a proper way to teach these on vector spaces. So that means you often see it when you come to like modules and rings and stuff. And then it looks quite a bit more complicated than this. And the complicated part is actually showing that, okay, here I made a choice of basis and then I made the vector space. And the hard part is just showing that this doesn't really matter at all. This choice of basis. Like these kinds of constructions and all of the things I want to do, these don't matter on this depend on this choice of basis at all, but it's a bit hard to write the tensor product without choosing the basis. And so that's the sort of complicated part with the tensor product is actually this invariant of choice of basis. But in terms of like just writing down what it is, it's just a span. You just take a basis and then it's just a span of these elements here. Okay, so now when we return to when we return to representations and tensor products of representations, it's going to be a bit different from groups and for groups and algebras. So in your exercises, you will have to show that if you have v of t ddt of v tensor w of t, then this is actually v dot of t tensor w of t plus v of t tensor w of t dot. So instead of, which is very different from the direct sum. Direct sum, you have just, if you take derivative, you have derivative of each part. If you differentiate in Rn, you'd have just you can just differentiate the coordinates. Whereas here, if you do a tensor product, then you have a product rule immediately. And that changes a little bit on how we define tensor products of Lie groups and Lie algebras. So for representations of Lie group, this is very similar to what we did with the direct sum. So if V pi and V sigma are representations of G, then we define pi tensor sigma of an element A applied to V tensor W as just the result of applying A, pi of A to V, and then tensoring that with sigma of A applied to W. So this is more or less what you would expect, whereas representations of a Lie algebra, if you have V small pi and sorry, here it should be W. W small sigma, representation of small g, then pi tensor sigma of x applied to V tensor W, that will be pi of x of V, so it looks a bit similar in the beginning, but then it's just tensor W, and then we need to add V tensor sigma of x W. So in this case, we don't get like a straightforward in each component. We need to do a sort of product formula when it comes to the algebra. Okay, so the final thing we need to talk about is that we need to talk about duals, but that's going to take 5 more minutes. So, and we have 2. So I'm going to stop the recording, and then I'm going to start it again. And then if you have to leave for a new class, then you can do that. And then you can watch this extra video later. And then if you can hang around for 5 more minutes, then you can watch it now and you don't have to watch it later.